randomly from 0, 1 to the n, so it's just a string of n bits. And a learner tries to learn that string x from a stream of samples, and the stream of samples is A1, B1, AI, BI, and so on for every time step. So, okay, I just started, so I will say there is, so I'm talking about the problem of parity learning first. X is a random vector in 0, 1 to the n that the learner tries to learn. The learner tries to learn it from a stream of samples, A1, B1, A2, B2, and so on, AI, BI. In each step, the learner gets AI, BI, where AI is just a random vector in 0, 1 to the n, just a random vector of length n. And BI is the inner product of AI and X modulo 2 over GF2. So this is BI. And the learner gets these samples one by one. A1, B1, A2, B2, and so on. He cannot go back and see what happened before. And the learner wants to figure out what is X. So this is the problem. And of course, there is a very simple and easy way to do that by solving linear equations. So in order to do that, the learner just have to remember a little bit more than n, let's say 2n samples, AI, BI, and solve linear equations over the coordinates of x and figure out x. So this is very efficient. It only uses about n samples, a little bit more than n samples. But in order to do that, the learner needs a memory of O of n squared, because the learner needs to remember n samples, each of them of length n bits, altogether n squared. Actually, n squared over 4 is probably the right constant. N squared over 4, memory of about n squared over 4 is sufficient. But what happens if the learner doesn't have a quadratic memory, if the memory is only a little bit smaller than n squared or even close to n? Can the learner still figure out what is x? So of course this is also possible, and one way to do that is by trying all the possibilities for x, and for each one of them you just check the next, let's say, 2n samples, and if it satisfies all of them, you know that with high probability this is the right possibility. If not, you move to the next possibility and so on. You just have to remember which possibility you are currently working on, and that's it. So you have to remember n bits, but you need an exponential number of samples. And now the question is if there is a better way. Suppose that you want to do that with less than exponential number of samples. Is it possible if your memory is less than quadratic or maybe even linear? And this, so about 2 years ago, Steinhardt, Valiant, and Dwager conjectured, and I solved about a year ago. So the theorem is, from about a year ago, is that any algorithm for parity learning requires either omega of n squared memory bits or an exponential number of samples. So if your memory is a little bit less than n squared, you will need an exponential number of samples to solve the problem. Or you can think about it that if your space is, so actually what you have, is if your space is limited, then the problem is intractable. It's infeasible to learn. You need an exponential number of samples, which is practically forever. So this is like lower bounds for learning under memory constraints. Previously, there was not even a linear lower bound on the space, and for any learning problem, not only for parity learning. So this is the theorem from last year. It has applications in cryptography. It's also related to complexity and pseudo-randomness. Another motivation might come from human learning, so that it can help to explain why good memory helps in cognitive processes and in learning processes. Also, maybe it's mainly interesting for machine learning. This problem came from machine learning, and it actually shows that a class of learning algorithms known as online learning algorithms cannot solve parity learning if their space is less than n squared. And so think of a learning algorithm that tries to construct some circuit for a problem, and there are some weights, and you see a sample, you update your weights. You see another sample, you update your weights, and so on. And then you never go back to the same sample that you saw before, except if you save it in your own memory. So these algorithms need space of omega of n squared to solve even the simplest problem of parity learning. So this is for parity learning. There was, in a follow-up work with Avishai and Gilat, we studied the problem of sparse parity learning. And what we proved is that even an algorithm for sparse parity learning with sparsity L an algorithm for sparse parity learning with sparsity L, which is a little bit larger than log n over log n. And by sparsity L, I mean that you know in advance that X is a string with exactly L ones. And L is, let's say, log n over log n or something like that. Even for that, you need either superlinear space, or a superpolynomial number of samples.
Is your randomness still uniform over all strings?
Yes, yes, you are still uniform over all strings of sparsity L. And also the AIs are uniform over all strings. Yes. So this is for any. So again, sparse parity, you have a vector x that you know that has exactly this number of ones. And what we are able to show is that you need either a superlinear number of memory bits or a superpolynomial number of samples in order to solve the problem. So this is what we are able to show. And then by reductions, we are able to show that learning linear size DNF formula, linear size decision trees, or logarithmic size juntas all require either superlinear space or superpolynomial time. So this is a superpolynomial number of samples. So this is what we are able to do. What I will talk about today is about a new work that study a more general class of learning problems, and in particular gives a new proof for the parity case, for parity learning, but not for sparse parities, only for parity. And so I study a general learning problem, and I present the problem as a matrix. So suppose that we have two sets, X and A are two finite sets. X will represent what we want to learn, and A, the space of the samples that we see. And we have a matrix M from A times X to minus 1, 1. And what I say that M corresponds to the following learning problem. Again, there is an unknown X that is chosen randomly from that set X. And you want to learn X by a stream of samples, A1, B1, and so on, where for each I, AI is a random element of the set A, and BI is just M of AI and X. So this is a general learning problem. X corresponds to what is called in learning the concept class, what we need to learn, and A corresponds to the samples that we see. So we can actually represent every learning problem, every standard learning problem by the matrix that represents the problem. And when we have such a matrix, I can consider the largest singular value of the matrix M, and I will denote it by sigma max. This is the largest singular value of M. So it is always the case that sigma max is lower or equal the square root of A times the square root of X. Square root of the size of A times the square root of the size of X. And the equality is when the matrix is constant. So sigma max is always between, is always lower than the size of A times the size of X to the power of 1/2. So this is the largest singular value. And the theorem, maybe I will write it here. Yes, exponential size sets. Exactly like here, the set is 0, 1 to the n. Actually, the best is to think of them as 0, 1 to the n. But it's more general. So the theorem is that for any such a matrix M, so suppose that sigma max, the largest singular value, is smaller or equal the size of A to the power of 1/2, square root of the size of A, times square root the size of X to the power of 1/2 minus epsilon. A little bit smaller than the maximum that it can get. So instead of having 1/2 here, we have 1/2 minus epsilon. Now, I have to say there are several ways to state that. You could have just divide by, so I prefer to have it in this form when the epsilon is on the X. Just it's easier for me for the proof. So suppose that we have any learning problem with that sigma max, with that larger singular value, then any algorithm for learning requires omega of epsilon n square space n is the logarithm of the size of x. Either omega epsilon n square space or 2 to the omega of epsilon n samples. Okay, so now it's for a general learning problem. If you know that the highest singular value is at most a to the half times x to the half minus epsilon, then any algorithm for learning, for solving that learning problem, even with exponentially small probability, requires either a space of omega epsilon n square or a number of samples exponential in 2 to the epsilon, exponential in epsilon n. Now, you should think of epsilon as a constant, but it's not necessarily a constant. You could even, the theorem is true even when epsilon is not a constant, but maybe it's the best to think of epsilon as a constant. Yes?
Well, you finish your thought.
So in particular, if you think about parity learning, in parity learning, you have Hadamard matrix, and for Hadamard matrix, epsilon is a half. So epsilon is a constant, and you get the same result as before. Actually, the constant that you have here is n square over 12. What you will get from that constant in the new proof. In the old proof, it was n square over 20, but Avishai noticed that it could be improved to n square over 10. So we are pretty close between the upper bounds and the lower bounds for the constant of the space. Yes?
So, did you suspect, or maybe it was part of your earlier theorem, the maximum singular value, is that kind of natural to show up in this context?
I think so. So, so this is kind of the norm of the matrix. And one thing about the Hadamard matrix that represents the parity learning is that the norm of the matrix is kind of the lowest that it could be for 1 minus 1 matrices. So, but the previous, so that's my next point. The previous proof was very specific for parity learning. It used very strongly the fact that it is parity learning, but somehow it seems unnatural because why only parity learning? Why not other problems? So for parity learning, sigma max is kind of the minimal that it can get, and then you okay. So what happens with other matrices that satisfy the same? Also, this largest singular value, it is related to all kind of other properties and other bounds that we have in computer science. For example, in communication complexity. For example, if you have a matrix of low discrepancy, we know that low discrepancy gives you small norm of matrix. This is actually the L2 norm. This is actually the norm of the matrix, the operator norm of the matrix, the highest singular value. So this is kind of close to bounds that we have in communication complexity that are also kind of general. We have like general lower bounds for probabilistic communication complexity in terms of properties of the matrix. So this is kind of one property that you consider. So more or less, this means that the rows of the matrices kind of tend to be orthogonal to each other. This is more or less the intuition, but there is the exact definition.
There is another one that's even closer to learning, which is the sign rank of the matrix, also going to, it's influenced by the sigma max, or the Forster result. And this is more or less, well, it has nothing to do with the time-space trade-off, but it is directly related to learning.
What did you say?
The
What
sign
kind of
rank. The sign rank. So what's
the sign rank?
The sign rank. So you can think of it as, but it's a any matrix is a communication problem. The question is, what can two players having an input of either side can achieve? How much communication they have to exchange in order to know what the value
Yeah.
So it's related to notions
So.
in a learning.
Okay, it's a good point. There is a notion of sign rank for which we also get lower bounds in terms of sigma max, of the highest singular value of the matrix.
So since you mentioned probability, is there a version of this theorem where you say if the probability is so much, or for example, you could have stated it as saying given so much space and given so many samples, you can give an upper bound on the probability of
This actually gives an upper bound. You cannot learn with probability better than exponential, than 2 to the minus constant times n. So by n I mean to log x. And actually in this talk, the best is to think about Hadamard metrics and parity learning. Don't even think about anything else. Everything I'm going to say generalize to this case. But it's not the point of the talk. I want to get a little bit into the proof, and the best is to keep in mind the parity learning. Everything translates immediately to any matrix that satisfies this condition. Yes?
So, is there a sparsity analog?
So I don't know how to reprove the results that we have for sparse parity learning using this technique.
Right. What about sparsity in the matrix M?
You mean that some points are 0, some points of the matrix are 0?
Yeah, I mean, you want it to be sort of close to, I mean,
Yes,
singular
so
value being
this is a good question. So you are referring to a case where the samples actually, where the distribution is not a product distribution, that the samples that you get kind of depend on the X itself, and not only the BI, also the AI. It's a good question. I think that there is a hope to do it using this method, but it was not done. But it's a good point. Okay. So again, you should think about it as Hadamard matrix. In parity learning, Hadamard matrix is the matrix of Fourier transform, so you get kind of Fourier coefficients. But anything I'm going to say will generalize to a general case where the operator norm of the matrix is small. So that's how you get this result. So again, in particular, we get a new proof for the Hadamard matrix, and for me it seems like kind of a more natural proof, although I wouldn't say that it's a simpler proof, but it seems to me like more like the right way to do that. Let me tell you a little bit.
Just one question. The size of A does not show up in the
The sign of what?
The size of A does not show up in the.
Yes, yes. Okay, so what I said is that there are several ways.
I see, because you put the epsilon only in the X.
I put the epsilon here, but it's an important point. So the maximum the maximum of epsilon n is not the size of x, but the minimum of the size of A and the size of x. So so this point you cannot see from this way to write the theorem, but the maximum lower bound that we can get is quadratic in the space in the minimum of log A and log x. So you cannot get. So this is like.
A is one. There's only one A.
Yeah, that's true, but I would have hoped to get something here that is log A times log x. I don't know how to do that. I get like the minimum of log A and log x square. And this is in the best case where I have a very good bound on the operator norm of the matrix.
So if epsilon is 0, you don't expect to have such kind of statement? Or
If epsilon is 0, then it's a constant matrix. So then in a sense you don't. Yeah, you cannot learn at all because you always get ones or minus ones. Yeah, but if you are asking, this is certainly not the only result that I expect that can be proved. So I'm sure that there are matrices with very high rank that you can still not learn. This is like one result that can be proved. Okay, let me tell you a little bit more about the history of the problem. So actually the history is not too long. There was the papers that started it, so one of them I already mentioned by Steinhardt, Valiant and Dwager, and there was an earlier paper by Shamir, and these are the first papers that studied the kind of memory samples trade-off in learning. They also refer to earlier works, but I think that earlier works did not actually state the problem in these terms exactly. They kind of talked about learning under restrictions of communication and information and things like that. So there was a paper by Shamir and a paper by Steinhardt, Valiant and Dwager. Also independently of my work, there was a paper by Dana Moshkovitz and Michal Moshkovitz, and they also prove exponential lower bounds for the number of samples for a large class of learning problems under some constraint on the space, but their bound on the space is at most 1.25 times n, where n is the size of x. So this is a linear lower bound on the space. And they have also a condition that is related to the condition that we have. It's stated in terms of mixing properties of the graph of the learning. So I just want to say that if you talk about lower bounds that are smaller than n on the space, then there are many earlier works, also in bounded storage cryptography that prove such bounds. Okay. So what I want to do next is to define the model that we work with. And this is the model of branching program. So what is a branching program? It's a directed acyclic graph with layers. And it has, so we think of a layers graph that has m layers with d vertices in each layer. And layer 0 is a special vertex that is called the start vertex. So d is the width of the program, which is like, you think of it as 2 to the memory size. So the memory size is log d. And so roughly speaking, each layer of the program represents a time step. And each vertex in a layer represents a state of the memory in that time step. So what we will have is that each vertex in the branching program has exactly 2 to the n plus 1 outgoing edges. So I think now of the size of x and the size of a as 2 to the n. I think of a Damar matrix of parity learning. So each vertex has 2 to the n plus 1 outgoing edges, one for each possible sample a, b, where a is in 0, 1 to the n, and b is the inner product of, supposed to be the inner product of a and x. So this is a branching program for the problem. You start from the start vertex, you read the first sample a1, b1, and you go to the next vertex, and then you read the second sample a2, b2, and you go to the next vertex, and then you continue reading until you go to the end. In the end, in the last layer, each vertex is labeled by some vector, which is the guess of the program of what is the correct x, given that we arrived to that vertex. So this in particular defines a computation path of the branching program. So you start from the start vertex, and you follow the samples and you get a computation path that depends on the samples, this we will refer to as the computation path of the program. So again, the program just represents all the possible memory states of the learning algorithm. The layers represent a time step. The different vertices in a layer represent the memory states of the learner. And the edges represent to which memory state we go in the next time step if we read a certain sample. And this gives you a computation path of the branching program. And finally, the last vertices have to give an answer. And this is the answer. This is the model that we study. It's the most general model that one can, in which one can study these problems. In particular, it's a non-uniform model. It doesn't care at all about computation. We don't care about computation time. We just care about memory size and number of samples. Yes?
So the matrix, you've been handed the matrix.
So you are yes, you know the matrix. You know the matrix.
The samples that you take, are you proceeding through the rows?
No, you just get a sample. They are random chase. So if you think about the matrix, the X represents a column of the matrix, and you just get random coordinates of this column. And this is the samples, AI, BI, and you just go, these samples define some computation path over the branching program. So this is the computational model. And now we can state our result in terms for that branching program. And the result is, for example, for parity learning, that any branching program for parity learning must be either of D larger than 2 to the omega of n squared, 2 to the omega of n squared, because like log D is the space that we have, or M would be larger than 2 to the omega of n. And if none of them happens, then the probability of success is exponentially small. So this is the theorem for branching programs, like stated in terms of a branching program.
So are both of the ends the minimum of log of A and log of X? Or
Yes,
both of them?
both of them. Yeah. It's you mean
Right. That.
here we have epsilon n here and epsilon n here. Epsilon n can be at most log A and at most log X. This is this we know. Okay, so we have a branching program and we have a computation path over the branching program. So now what I'm going to do, I'm going to start with giving you something about the proof. I will not do the entire proof, of course, but I will. I hope to tell you something about the proof. So as I said, for the proof we consider branching programs, and we have the computation path over the branching program. But now what I'm going to define, I'm not going to define it exactly. I'm just going to say that in the proof there is a notion that I call the truncated path, tau. Tau is the truncated path. So what is the truncated path? The truncated tau. So what is the truncated path? The truncated path is the same as the computation path, except that sometimes it stops. When several things, bad things happen, I just decide to give up and to stop. And so this is the truncated path. There is an exact definition of what it means. For now, just you have to know that it follows exactly the computational path, except that sometimes it stops. I define in the proof exactly the conditions of when it stops before reaching a leaf. And what we prove is that the probability that tau stops before reaching a leaf is exponentially small. So for all practical purposes, tau is exactly as the computation path, because you only stop with exponentially small probability, and we don't care about exponentially small probability. But it's really important to work with the truncated path. And the reason is that in the proof, we will work with probabilities much smaller than exponential. And we will prove things that are not true for the computation path, for the computation path, but they will be true for the truncated path because of the special properties, because of the way that we will define the truncated path. So this will be important. Okay, so we have the truncated path. After we have defined the truncated path, we can define for each vertex in the branching program, we define by the probability for V. This will be the probability that tau reaches V. This is the probability for a vertex V, just the probability that the truncated path tau reaches V. And we define the probability for x conditioned on V. This is a distribution. The distribution of x conditioned on V will be the distribution of x conditioned on tau reaches V. And the same for edges.
X is a leaf.
Sorry?
X is a leaf.
X is the random.
X is the random string.
Oh, the true answer.
Yes, so you have your path T, and we define by the probability of V the probability that tau reaches that vertex V, and Pxv is the distribution, assuming that you reached the vertex V. What is the distribution of x? This is Px conditioned on V. This is just a notation. Now, using this notation, I want to consider the L2 norm of that distribution. And I'm going to define the L2 norm with expectation rather than sum. It's not important, just for notations. So this is the expectation over all x prime of Px conditioned on V of x prime square root. So this is the L2 norm of the distribution Px conditioned on V. I did it with expectation. It could be done with sum. It's just a normalization. It's really not important. So this is the L2 norm of the distribution. And now I'm going to define a significant vertex. V is significant if the L2 norm of Px conditioned on V is larger or equal some threshold that 2 to the delta n times 2 to the minus n. So what does it mean? So if Px conditioned on V was the uniform distribution, you have the L2 norm is 2 to the minus n. So the L2 norm of the distribution can be higher and higher. And I put the threshold on 2 to the delta n, where delta is some constant that I'm going to optimize at some point, not in the lecture, of course. And a significant vertex is when the L2 norm is already large, is already larger than something. This is a significant vertex. And so intuitively, in order to solve the problem, you must reach a significant vertex. Because a significant vertex intuitively is a vertex for which you already have a non-negligible amount of information on the x that you want to solve. So to solve the problem, you must reach a significant vertex. And what we are going to prove is that the probability that tau, the truncated path tau, reaches a significant vertex is exponentially small.
This is assuming that D is small.
Yes, we take a branching program with, we take for a contradiction, branching program with, let's say, D small d and small m, d smaller than 2 to the omega n square, and m smaller than 2 to the omega n, and then we prove that the probabilities that such a, that tau reaches a significant vertex v is exponentially small. And that's it. So you prove that this is exponentially small. If you don't reach a significant vertex, you cannot solve x, except with exponentially small probability. So that is, the program cannot actually solve x, except with exponentially small probability. So the question is how to prove this. So this is, of course, the hard proof. So the way we do that, we prove that by the union bound. So for any significant vertex S, we prove that the probability that tau reaches S is lower or equal to 2 to the minus omega of n squared. For any significant vertex S, the probability that tau reaches that particular significant vertex is 2 to the minus omega of n squared. And now when we take the union bound over all the vertices of the branching program, you get something exponentially small.
So even when you write exponentially small, there is exponentially n squared. The statement, yeah.
This is exponentially n squared. Yes. Exactly. Yeah. So this is for tau, not for the computation path. It's not true for the computation path. So now you can see why we need the computation. This won't be true for the computation path. It's true for tau. And you see that although we prove that the probability that tau is exponentially small, so exponentially small, it seems as we could take the computation path, but no, we work with probability that are much smaller than exponential. So it's really important, at least for that proof, to work with tau rather than with the computation path. So these probabilities are much smaller than what we have here. This is just exponentially small, 2 to the minus omega of n. So you could think of it as the probability that the computation path reaches S conditioned on some event. So there is like a bad event, you assume that it doesn't happen, then the probability is this. And of course, this is what is hard to prove. And I will show you something about how the proof goes, of course, not the entire proof. How do we prove that the probability that tau reaches a significant vertex is so small, 2 to the minus omega of n squared?
By induction on the levels of the
There will be, the main part will be by induction, so yes. Okay, so what we are going to do is we're going to measure the progress that, so this will be the induction part. We're going to measure the progress that the branching program makes towards reaching S, towards reaching a distribution similar to Px conditioned on S. And the measure that we will, the progress measure that we will consider, let's denote by Li, the ith layer of the branching program. We're going to define the function Zi to be the sum over all the vertices V in the layer Li. For each one of them, we take the probability of V, and we multiply it by the inner product of Px conditioned on V and Px conditioned on S to the power of n. So for every vertex V, we consider the inner product between the distribution Pxv and Pxs. This measures how close these distributions are. But we take it to the power of n. And this n is important to get the n square there. Otherwise, without this n, we would have gotten only 2 to the minus omega of n there. We take like an average, we take like an expectation with, it won't be exactly an expectation because there is a probability that tau stops before that layer at all, but it's a weighted average of the probability for a vertex times this function. So this is like a function in which we measure the progress made towards reaching the vertex, S. And I have to say this inner product is just, I take it with sum. Actually, in the paper, I take it also with expectation, but I think in the talk, it's easier to think about it as the sum. So it's sum over all x prime of P x v of x prime times P x s of x prime. So this is the inner product. This is the progress measure that I'm going to define, how close we get to the vertex S. So now the main step, and this is the inductive step, the induction, is that we prove that this measure grows very slowly. When you go over the layers of the branching program, it goes very slowly. So what we prove is that Zi plus 1 is smaller equal Zi times 1 plus 2 to the minus omega of n plus like 2 to the minus omega of n plus 2 to the minus omega of n squared. So you just multiply by 1 plus something exponentially small, and you add something exponentially small. So the progress that you make is very, very small from one layer to the other one. Now, suppose that we prove such a theorem, that the progress is very, very slow over the layers of the branching program. Now, it's really easy to show that Z0, to calculate actually, is 2 to the minus n squared. And this is because for the 0 vertex, the distribution of x is uniform. So you have a uniform distribution, inner product with any distribution gives you 2 to the minus n, and you get 2 to the minus n squared. So Z0 is 2 to the minus n squared. Now, let's assume that S is in layer M. Suppose that S is in layer M. then what you know is that Zm is at least the probability for S times the inner product where V equals S. Pxs, Pxs. And Pxs, Pxs, we have a bound on that because we know that it's, so this was with expectation instead of sum, but we have a bound 2 to the delta n times 2 to the minus n. And when you substitute, you get the probability of S times 2 to the 2 delta n square times 2 to the minus n square. And this is just because S is significant. And we know that significant S, we define it as L2 norm large. So you get that the probability of S times 2 to the omega n square times 2 to the minus n square. So from that inequality, from that inequality, since the progress is so small, you know that Zm is at most 0. The progress is very small, so Zm would be at most twice Z0 because the progress is exponentially small. And from these two things together, you get that the probability for S must be 2 to the minus 2 delta n square. So this is 2 to the minus n square. 2 to the minus omega of n square. So this is the way you get the bound on the probability of S. You just know that for Zm, you know that Zm is bounded from above by the probability of S times something large, and you know that it's bounded. Zm is bounded from below by probability of S times something large, and from above by something small. So the probability for S must be small, very small, 2 to the minus omega of n square, and then you can apply the union bound. So this is kind of easy, and the hard thing is to prove that the progress is small, that you make the progress is very slow. Okay, so how do we do that? So I don't know what to erase. Maybe I will erase.
Want to keep the top line of this one?
Yes, probably. I can also write there, but so I want to compare Zi to Zi plus 1. So Zi talks about the ith layer, and Zi plus 1 about the I plus 1th layer. So I want to see what happens in between. So I'm going to define Z prime to be the sum over all these here between I and I plus 1 of the probability for the edge. The probability for the edge is the same as just the probability that tau traverses that edge times this px conditioned on E, px conditioned on S to the power of n. So I do the same as I did for the vertices, I do for the edges between layer I and layer I plus 1. Probability for, yes, yes, Px conditioned on E is just a probability for X conditioned on the event that tau traverses the edge E. And prob of E is the probability for the edge E. So it's exactly the same expression, only I sum over the edges between layer I plus 1 and layer I. And now I'm going to prove something. I'm going to prove actually two things. The first is that Zi plus 1 is smaller equal z prime. This is easy. This is by a convexity argument, just because just because you, for each vertex in layer I plus 1, you just consider all the edges going into it, and you do a convexity argument because this function is convex. So it's really easy to prove that zi plus 1 is smaller equal z prime. So this is easy. But what you need to prove, which is harder, is that z prime is smaller equal zi times 1 plus something negligible plus something negligible. So this is the hard part. So to prove this, okay, let me do it. So what we do, if this is layer I, we take one vertex in layer I, and we look on all the edges that are going out of it. And in Zi, we have one term that corresponds to that vertex V. So that term is just prob V times pxv, pxs to the power of n. So we compare this term to the terms of the edges that are going out of that vertex V in this sum. So what we want to prove is that sum on all the edges E that are VU, that are going out of V, of the probability for E times the inner product of Px conditioned on E, Px conditioned on S to the power of n. This is the sum of all these edges in this expression in Z prime. We want to prove that this is smaller equal the probability of V times Px conditioned on V, Px conditioned on S to the power of n. All this times 1 plus 2 to the minus omega of n plus O of 2 to the minus n squared, something like that.
The way the significance of S enters in just by the by the fact that there is a strong.
I already used the significance of S here, but I will need.
No, this is true for every S or for significant?
For significant S. For significant S and for the right definition of tau.
Yeah, it has to, but the only way it can come in is through the definition of tau. You don't know
Yes.
what it's like, really. You're just looking at the layer.
No, but you also have here the distribution Px conditioned on S, and you know something about this distribution. But you are right. It's not. It will come because of the definition of tau. But anyway, what I'm trying to make is to compare Z prime to Zi. I'm comparing it vertex by vertex. Each vertex V, I'm going to compare to the edges going out of it. So we have on one side the probability of V times the inner product of Pxv, Pxs to the power of n, and on the other side the probability of E, the inner product Pxe, Pxs to the power of n. And to compare these two, what you need to actually do is to divide by Pxv, Pxs. So you have to kind of compare the ratio between Pxe, Pxs, and pxv, pxs. This is what you have to bound. Kind of to show that this ratio is close to 1. If you show that if this ratio was close to 1 always, then you are fine, very close to 1. So, okay, so now since I don't have time, I will not do it. I will just say a few words. Well,
I know you want
I did.
but I want to get it.
I didn't think that Avi will let me stop here. So, okay, so again, we have to compare the left-hand side. Sorry?
Have you used the fact that sigma max is?
No.
I still didn't use it,
Okay.
but I don't even think about sigma max. I think about parity. About so it will be like Hadamard matrix. But no, I still haven't used it. So it is used in the proof, for example, that the probability that tau stops is exponentially small, but I didn't even said what is the definition of tau. But anyway, we will get to what exactly we need to do. So we have on one hand, we have this term pxv pxs to the power of n, and on the other side pxe pxs to the power of n. So if we could show that the ratio is kind of almost always close to 1 between pxe pxs and pxv pxs, the inner products, then we are fine. If the ratio is close to 1, we know that the right-hand side of the equation, we know that the right-hand side of the equation cannot be much smaller than the left-hand side. Yes.
And that sort of is that ratio must be related then to the probability that your tau condition trims too many or too few of the edges out of feet.
It's true. It's true. This ratio, to prove that it is close to 1, we must use the properties of tau. And I will try to just hint how I do that. So let's consider the function f that is pxv times pxs.
What do you mean times?
Times, it's a function. Distribution times distribution.
Evaluated on at the same point.
Yes, yes. So the inner product takes the sum of all the elements of this function. So this inner product is just the L1 norm of that function. Now, what is pxe, pxs? So think about it about Hadamard matrix. What is the distribution of x conditioned on E in terms of the distribution of x conditioned on V? So E is just an edge, and an edge is labeled by AB, and which means that you go there only if you satisfy the equation AX equals B. So this will actually be the restriction of the distribution PXV to a half space, normalized. Forget about the normalization for now. Normalized with something that is close to a half, but not always a half, depending on the Fourier coefficient. So when you look on PXE times PXS, you actually get the Fourier coefficients. You actually get the Fourier coefficients of f. So actually, this thing you can actually show. If I forget about the normalization of PXE, and I will forget for now about this normalization, this is actually exactly equal or very close to, because of the properties of tau, but forget about it, the Fourier coefficient of f with something that is determined by E, normalized by the zero coefficient.
But the numerator is going to be
Yes.
The
No.
numerator, so this equals what? The numerator of this expression?
No, this is after normalization.
No.
This is after normalization. The whole thing here, except under the assumption that we didn't really forget about the normalization of Px conditioned on E, is going to be very similar to the Fourier coefficient of f normalized by the first coefficient. This is what you get. So, but I won't do things in details. I will just tell you the ideas. So, in order to bound the Fourier coefficients to show that in general they are close to 1, you need to bound the L2 norm. This is not the Fourier coefficient. This is 1 plus the Fourier coefficient, like a half plus the Fourier coefficient or 1 plus the Fourier coefficient, because you restrict it to a half space. You didn't reduce the other side of the half space. But it doesn't matter. It's just the point is that this is related to the Fourier coefficients, and in order to bound it, you need to bound the L2 norm of f, of the function f. So this is what we need to bound the L2 norm of the function f normalized, after you divide by, so actually what you have to bound is the L2 norm over the L1 norm. So now I will not do anything. I will just tell you more or less how I do that. How do I bound the L2 norm of f over the L1 norm of f? So these are just two functions. They can be almost not correlated. So when you take the product, you can get something very small with very low L1 norm. So you don't know almost anything about this function. So how do you do that? So the way I do that is as follows. First, I claim that the F1 norm can be assumed to be large. Otherwise, all this term is too small and can be removed from both sides of the equation. You don't care about it. So the L1 norm is large enough. But now still you have Pxv times Pxs. How do you bound the L2 norm of this expression? So you could bound the L2 norm of Pxs because okay, so what you do, so you could bound because when you get to a significant vertex, you stop. So you could bound the L2 norm of Pxs, but you don't know about, you can also bound the L2 norm of Pxv, but then it doesn't give you any bound to. So what you do, you bound the L2 norm of this and the L infinity norm of this. How do you bound the L infinity norm of this? You just force tau to stop if Pxv of x is too large. So now we get to the property of tau. So tau stops in several cases. First, if tau of x is large, then tau also stops. And this means that you can kind of ignore the part of the space where Pxv is too large and only consider the part of the space where Pxv is small. So you get a bound on L infinity here and a bound on L2 norm here, which gives you a bound on the L2 norm of f itself.
This is some x bar. This is the value of.
This is the same x.
Well, x.
The same x. The same x. You consider you reached a vertex v. You consider the distribution of x conditioned on v,
Yeah.
and then tau just kind of it's cheating. It looks what is the correct value of x, and look if pxv of x is too large, then it stops. And the reason it stops, because if you stop, then you don't continue to any of the edges, and then you don't really need to count that in the sum above.
What is the, so it's the same x means you have a distribution. So pxv is a distribution.
It's a distribution.
Right. So
And you plug in the correct x. The correct x. And if it's too large, you stop.
what is the correct x? I'm still,
There is a correct x somewhere that the branching point.
pxv is a distribution.
Yes.
It's a distribution on initial on x.
It's a PXV doesn't know anything about there is also a correct x. PXV doesn't know the correct x. There is a branching program that reaches some vertex v. Conditioned on the event that it reached v, there is some PXV. Now you look what is the correct x. And if it happens that if it is in a place where PXV has a large value, you just stop. You ignore this case. You define this as a bad event. So it's an event, right? It's an event. The PXV of x is large. You define it as a bad event.
For which this is large.
Yes,
It's just
you
all the
stop.
x's there.
Yeah, you just
So
stop
this
there.
should be- So large is just exponential in n. It's some 2 to the minus.
It's like 2 to the constant times n times
Not
some
squared, yeah.
times what it was supposed to be. Like 2 to the
Yeah,
delta
yeah.
n. Not exactly, but more or
You
less.
can be cautious and say just if there is some x prime for which this is large, and you also stop.
I
Is it okay?
couldn't because, no, it wouldn't be okay. Because then I wouldn't, I can't prove that you stop with exponentially small probability. So it's all about the stopping rules of tau. I stop if I get to a significant vertex to ensure that px conditioned on s is small, the L2 norm. I stop if px conditioned on v of x is too large, and then I ensure that the L infinity, effectively the L infinity norm here is small. I can ignore the part where it's large. And there is another stopping rule that is related to the normalization of px conditioned on E. I said that the normalization is kind of determined by the Fourier coefficient of px conditioned on v. So if tau sees that it's about to traverse an edge for which the normalization is too different than a half, is too high or too small, it just stops. So there are like 3 stopping rules for tau. Each of them I can prove that happens with, sorry? So
Isn't it a bit circular? They have the distribution of x.
it is very circular. So what you do it layer by layer. You define whether you stop or not for that layer. And if not, you continue tau by the computational path. Then you decide. So you have to define them together. I didn't do that in the lecture, but you're right. You have to define tau together with them together, layer by layer. For each layer, you decide if to stop or not. If not, you define tau to go as the computation path, and then you have the px conditioned on v and the probability for v. It is very circular otherwise.
So the probability that tau stops early is exponentially small is also proved by induction
This you don't need induction. This after you made all the definitions.
Exponential again, there is also exponentially n.
Well,
The probability that tau stops before reaching a v.
it's exponentially small in n. Yes, in n. So what you have is like 3 rules when tau stops. One to bound the L2 norm here, one to bound the L infinity norm here, and one to bound the normalization factor here to be very close to a half. So you define these stopping rules, and now what you are able to prove that tau stops altogether with exponentially small probability If it doesn't stop, then it continues like the computation path, and then you are able to prove that the progress function for every s grows very, very slowly. Then you use the union bound and get the results. Now, one interesting point here is why I raised to the power of n. So the reason that I raised to the power of n is that there are like exponentially small number of bad edges. These bad edges increase the pxe, pxs would be like a factor 2 more than pxv. So the ratio between this and this will be like a factor of 2. And when you take 2 to the power of n, it cancels the exponentially small probability. So n is kind of the maximum power which I could take. Actually, a constant times n, but the constant is close to 1, so it's fun. So that's why I took n. I couldn't take anything larger. I could take something smaller, but then I would get a lower band that is not as good. But this is the main point, to be able to work with raising to the power of n. Otherwise, you only get, you won't get a quadratic bound, only something like super linear.
Without saying what the bad edges are, do they actually exist? Or can you only prove that they might exist and there could be this many, so I have to just kind of...
So I think they exist, yes, they exist.
This
So
is kind of a situation where you are doing parity learning and the first, n samples